Hello everyone, Mr. Fawcett here, and we are about to start a new unit in our AP Calculus AB adventure. We just finished up a unit on limits and the accompanying concepts that go along with those, and today is going to be our entry point into the concept of derivatives. So we're not going to do much calculus today. We're actually going to go back and review some concepts that you've talked about in almost every math class you've taken up to this point, going back to pre-algebra or maybe even some middle school math. And then as we get into later videos, we'll talk about the new tools and strategies and techniques that go along with understanding and finding out what these things called derivatives are, which is probably a new word for us. So let's get started with a little introduction problem. It says Jake's mom asked him to pick up some things for dinner at the store. The store is 5 miles away, and it took Jake 10 minutes to get there. The speed limit on the road to the store is 35 miles per hour. Part A asks us to find Jake's average speed in miles per hour on the way to the store. So pause the video. You can answer part A, and you can actually answer the rest of the parts in this page, A, B, and C. And then we'll have a thorough discussion about all the parts. Okay, so first things first, let's find his average speed, and we're asked to do that in miles per hour. Now, miles per hour, another way we can write that is miles divided by hours. Okay, so miles per hour, that per is referencing division. So we know the number of miles he traveled, that's 5. We don't know the number of hours, at least not directly, but it does tell us how many minutes it took. It says it took him 10 minutes. So again, to convert minutes to hours, we're not going to go through this in too much detail, but 10 divided by 60 gives us 1/6. So it took him 1/6 of an hour to get to the store. Now, if we're dividing by 1/6, that means we are actually multiplying by 6. So we end up getting 30 miles per hour. And again, we just usually write that as 30 mph. So his average speed was 30 miles per hour. Part B says Jake ended up getting a ticket on the way to the store. How is this possible? Did the police officer make a mistake? So remember, it said that the speed limit on the road to the store was 35 miles per hour. Now, Jake's average speed was 30 miles per hour. So is it possible that he still got a ticket? Is there, if his average speed is 30, how could he possibly get pulled over for going 35? Well, just because his average speed is 30, of course, doesn't mean that his speed at every single point in time was 30 miles per hour. We could assume that maybe Jake slowly pulled out of the driveway, then he slowly sped up his car, and maybe he ended up getting to 50 miles per hour on his way to the store. And then when he was pulling into the parking lot, he slowed it down. But his average speed ended up being 30 miles per hour. So just because his average speed is 30 doesn't mean that he may have sped up past 35 and then slowed back down. Maybe he was stopped at a stoplight, etc. So it is possible. I went ahead and just wrote down the explanation while I paused the video just to save some time. But it is possible because the average speed doesn't tell us his speed at each moment in time. And that actually gets to question C, which asks, what would you have liked to known to make that decision about whether the cop should have given him a ticket or not, or whether he was traveling more than 35 miles per hour. And for that, you would just need to see a graph of his speed versus time. So to be able to see at every single point in time, did his speed ever get higher than that 35 mile per hour speed limit? All right, let's move on to page 2. So here we're being asked to draw 2 different graphs of Jake's possible journey. It does say note what variables lie in each axis, so let's review those. X is time in minutes, and the y-axis is distance traveled in miles. The reason it says draw two possible graphs is because I want the first graph that you draw to be a graph that would represent a journey where he would not have gotten a ticket. Or you could say where the officer would have made a mistake in giving him a ticket, because it would have been impossible for him to have gone more than 35 miles per hour. Now, the second graph that you draw, I want it to be representative of a journey where he would have gotten a ticket, or where he did go more than 35 miles per hour. So take a shot at drawing both of those graphs, and then we will jump back here for a discussion. Okay, the first graph that I'm going to draw is going to represent the time where he should not have gotten a ticket. So I know my starting point. When t equals 0, he hasn't gone anywhere, so his y value is going to be 0, the distance traveled. And okay, so let me just make a clarification. It is possible that he doesn't take the most direct route to the store, right? So the store is 5 miles away. We're assuming that he just goes on a straight path there. It is possible that maybe he makes a wrong turn and ends up going further away from the store at some point. We're just going to assume that if he's moving, he is moving towards the store. Just to clarify, because I know we could have said, well, I have a graph that maybe looks a little different, or other things are possible. I get it. We're just making a simplification. Now, if I just connect these points with a segment, okay, that's one possible representation of his journey. And if it's a segment that doesn't change, right, there's only one segment here, there's just one slope for his entire journey. So the average slope is going to be, he's going to be traveling the same speed for his entire journey. Which again, I know you could say, well, how does he start the car going 30 miles per hour? And shouldn't he slow down at the end? Yes, essentially, but we're just going to make a simplification and say it's possible for him to just start at 30 miles per hour and end at 30 miles per hour. I've been saying 30 miles per hour, and that's because that's what the slope of this red graph is. We've already proved that up above because we did the work for it, but we can do it again and talk more about slope notation and the slope formula. So if I wanted to find the slope of the red line, right, maybe you're thinking rise over run, but I try to stay away from those words. I prefer change in y over change in x. Using change in y over change in x assures that you're not going to switch up the x and y values, right? So if you say rise over run, it's possible that you still stick your x values in the numerator and your y values in the denominator. But if you're thinking change in y over change in x, it's more unlikely that you're going to do that. The change in y here is 5 miles, and our change in x is 10 minutes. And this should look familiar because this is what we initially came up with for the first part of this problem. We converted minutes to hours. And we got 1/6 hours. And then that gave us 30 miles per hour. So the slope of this red line is 30 miles per hour. And because it's the slope of this segment, because this is a segment, that means that he was traveling the same speed the entire time. So it would have been impossible for him to be going more than 35 miles per hour, and he should not have gotten a ticket. Now let's think about a graph where he should have gotten a ticket. It's going to have the same initial and ending point. But let's say for the first 3 miles, it only took him 3 minutes. Then he waited at a stoplight for 2 minutes, and then he continued his journey to the store. So right away, we see that there's 3 different slopes here because there's 3 different segments. And it's pretty clear that along this interval 0 to 3, he's going faster than 30 miles per hour, right? Because the slope of the blue segment is steeper than the slope of the red. But we don't know exactly how much faster until we perform the slope formula. So let's do that. Again, we'll start with our change in y over change in x. Let's make sure that's a clear y. The change in y over this interval is 3 miles. Again, I'm just doing from 0 to 3 on the x-axis. And the change in x is 3 minutes. Now we do need to convert minutes to hours. So I'm going to have 3 miles divided by 1/20th of an hour. And that's going to give me 60 miles per hour. Again, because this is a segment, that means his speed is constant. So from 0 to 3 minutes, he was going 60 miles per hour. So it was reasonable for the officer to give him a ticket if the speed limit was 35 miles per hour. So this should have been nothing new, right? We found slopes of lines all the way back in pre-algebra or even before then. But calculus is where this becomes a little different. So let me throw another graph at you. So this green graph is a third possible journey. Now the difference between the green and the other two graphs is that the green graph is curved. It's not made up of segments, which means that his slope is constantly changing, right? For the blue and the red segments, it was very clear to see at what points his slope was constant and at what points his slope changed. For the green graph, it's not clear when the slope changes. It looks like it's changing constantly, but because it doesn't look like it's made up of segments, the slope is not constant. So that still means we can find average speeds, right? Because I could still find the slope between these 2 points if I wanted to find, let's say, the average speed from 0 to 3. But that wouldn't tell me what the speed, that wouldn't tell me what his speed was at, say, 1.5, right? This dotted green line, if I make it a line, just tells me his average speed. But it doesn't tell me the speed at this point, right? We wouldn't know what the speed was there. We wouldn't know what the speed was here. We would just know the average speed between 0 and 3. And we have a word for this dashed line. It's called a secant line. In pre-algebra, algebra 1, algebra 2, pre-calc, that's what we've dealt with when we've found slopes, right? We found the slope between 2 points. In calculus, we're going to look at ways to find the slope at a single point. So in calculus, we could find the slope at this single point or at this single point. The only time we could do that in our previous math courses was when those were points on a segment. So if we had a segment, we knew that the slope for all of these points was the same, because the slope was constant over the entire segment. But when our graph is curved, the slope is constantly changing, and we don't have tools yet to figure out the slope at each of those individual points. But that's where we're moving towards. All right. So again, just to rephrase all of these things before we stop this part 1. Up until this point, we've been able to find the slope between 2 points. It doesn't matter how close or how far apart they were, we could always do the change in y over change in x. Moving forward, we're going to look at ways to find the slope at a single point on a graph. All right, this has been Mr. Fawcett with part 1. Stay tuned for part 2.